Most people imagine it as a space completely devoid of air. But if you delve a bit into quantum mechanics, you'll learn that even in a space with nothing, quantum fluctuations still exist. Hence the phrase, "the vacuum is not empty." So, theoretically, does a truly absolute vacuum exist? And how far has scientific understanding of the vacuum progressed today? In this discussion, we'll break down the concept of vacuum into 7 levels. Let's see which level your understanding reaches. Level 1. Vacuum, no particles. There are actually many real-life scenarios involving vacuum, like vacuum packaging or vacuum-insulated cups. Industrially, any environment with pressure lower than 1 standard atmosphere can be called a vacuum. Depending on the degree of pressure, they are classified into different levels like low vacuum, high vacuum, and ultra-high vacuum. For example, the Magdeburg Hemisphere experiment learned in middle school, where teams of horses couldn't pull apart the metal spheres, demonstrates a high vacuum environment inside. In most people's imagination, if we remove all the air from a container, leaving none behind, that should be a true vacuum. But this kind of vacuum can only be said to have no air. It doesn't mean truly empty. Just like we equate space beyond the atmosphere with a vacuum environment, but in reality, space contains various radiations and particles like cosmic rays. At the very least, the fact that you can see light means there must be photons there. Even if you block all external radiation, including the cosmic microwave background radiation, the container itself will still emit radiation. After all, as long as it's not at absolute zero, everything theoretically has thermal radiation. So, if there were an ideal environment that was completely sealed, had not a single particle inside, and itself produced no radiation, it could indeed be considered an absolute vacuum in the electromagnetic sense. It's just that such a vacuum clearly doesn't exist in reality. Level 2. The vacuum is not empty. Virtual particles. Although in electromagnetic sense vacuum doesn't exist in reality, let's assume such a vacuum exists. Is there really nothing inside? Of course not. While real particles might not be present, there are still virtual particles inside. What is a virtual particle? I believe no matter how much you know about quantum mechanics, you've probably heard of the Heisenberg uncertainty principle. It can be said to be one of the core, most fundamental principles of quantum mechanics. Simply put, it states that for certain specific physical quantities, like position and momentum, or time and energy, it is impossible to simultaneously know the precise values of both. Take position and momentum. When we precisely measure a particle's position, its momentum cannot be accurately measured, and vice versa. Note, this inability to measure accurately isn't due to technological limitations or being locked by protons. It's theoretically impossible. This is also why the principle's name was changed from the indeterminacy principle to the uncertainty principle. Similarly, for the pair of physical quantities, time and energy, we cannot determine both simultaneously. If we confine time to an extremely short scale, then energy becomes very uncertain at that moment. This phenomenon holds true even for the vacuum. Within an extremely short time, the vacuum's energy might not be zero. Some energy can appear out of nowhere, manifesting as the random generation of a pair of particle-antiparticle particles in the vacuum. This pair of particles generated from nothing is called a virtual particle. Why virtual? Because it only exists on paper. That is, during calculations, it was found that if one assumes these 2 particles exist here, describing the entire process becomes very convenient, and crucially, these 2 particles quickly annihilate each other and disappear. The energy that appeared out of nowhere is returned to the vacuum. Everything is as if it never happened. This is the so-called vacuum quantum fluctuation. From this, we can see that energy conservation isn't an absolute iron law either. It mostly holds true from an overall perspective. So, macroscopically, the vacuum is just vacuum, with no particles inside, but microscopically, the vacuum is filled with virtual particles generated by quantum fluctuations. Therefore, we say the vacuum is not empty. Level 3. The vacuum is not empty. The quantum field. You might have a question. Since virtual particles are just imaginary concepts used in calculations, can they be considered real? Correct. Virtual particles are just an intuitive concept imagined for calculation purposes. They are not real particles that truly exist. However, in terms of their physical significance, the interactions involved are indeed real and tangible, because the influence of virtual particles on real particles can be zai da tanka data. Therefore, virtual particles can be considered to exist, just not in the form we typically imagine. In fact, as quantum mechanics developed into its later stages, physicists combined quantum mechanics, special relativity, and classical field theory to create a masterful synthesis, quantum field theory QFT. In quantum field theory, both virtual particles and real particles can be seen as ripples or excitations in a field. The difference is that real particles are stable excitations that can persist and propagate, making them directly detectable. Virtual particles, on the other hand, are short-lived. They generally just pop in and out, briefly come out for a sauce and go back. We can only confirm their existence through indirect phenomena. Therefore, from the perspective of quantum fields, whether it's real particles or virtual particles, the vacuum is always accompanied by one thing, the quantum field. Level 4. The vacuum is not empty. The relative vacuum. Just as there is no absolute time in relativity for space, perhaps the vacuum is not absolute either. As quantum field theory matured, physicists began considering how to integrate general relativity into it. While exploring quantum field theory in curved spacetime, physicists theoretically discovered a strange possible phenomenon. When you undergo acceleration in a vacuum at absolute zero, you will find that this vacuum actually has a temperature. But this temperature is only from your perspective. For an external observer, this region of space remains a vacuum without temperature. This peculiar phenomenon, where the temperature depends on the chosen reference frame, is called the Unruh effect. In general relativity, acceleration and gravitational fields are equivalent equivalence principle. Thus, near some extremely strong gravitational fields, like those of a black hole, the Unruh effect might cause the black hole itself to produce thermal radiation, meaning the black hole has a temperature. If a black hole has a temperature, it must inevitably radiate energy. Where does this energy come from? Yes, converted from virtual particles. This is the true origin of Hawking radiation. Therefore, whether the vacuum is empty, whether it contains only virtual particles or also real particles, can depend entirely on how you choose your reference frame. A side note, why don't we usually consider the reference frame issue when discussing vacuum? Because, although theoretically, there is no absolute reference frame, one thing is quite special and is often used as a standard reference in large-scale problems like cosmic evolution, the cosmic microwave background CMB radiation. People often ask, relative to whom is the age of the universe measured? Here, you can understand it as relative to the background radiation. It is the universe's own time, also called cosmic time. Since Earth's gravitational field is very weak, relativistic time dilation effects are extremely tiny. Therefore, we can place it and the background radiation in the same reference frame. The same goes for the vacuum. Usually, the influence of the Unruh effect on the vacuum is very limited, even undetectable. Level 5. True vacuum versus false vacuum decay. As we said earlier, various quantum fields exist in the vacuum. For most quantum fields, they have a lowest energy state called the ground state. A field in its ground state has the lowest energy and is most stable. But in our universe, there is one field that is currently not in a stable ground state. It is the Higgs field, which gives elementary particles their mass. Although the state of the Higgs field has been maintained for 13.8 billion years, since it is not in the most stable ground state, this stability is only temporary. It could potentially drop to a lower energy state at any time. So, you can consider that the vacuum in our current universe is actually a false vacuum, perhaps one day, the potential energy of the Higgs field somewhere suddenly falls to a lower state. At that moment, the false vacuum would become a true vacuum. Afterwards, this change would spread out in all directions at nearly the speed of light. This phenomenon is called false vacuum decay. Vacuum decay is somewhat similar to the effect of the asteroskirkoring, or Xiangbo, is a term from Liu Cixin's The Three-Body Problem trilogy, referring to a hypothetical dual vector FOIL that reduces dimensionality, collapsing 3D space into 2D, asterisk dimensionality collapse. The entire space plummets towards the dimensions at the speed of light and does not stop. But unlike the dual vector FOIL, vacuum decay would cause many elementary particles to lose mass. All matter in the universe would consequently be annihilated, and the entire framework of physics would be completely rewritten. In short, when the Higgs field drops to a lower ground state, space will become a true vacuum. Level 6. Different vacuums. Vacua in string theory. Although quantum field theory is sufficient for most situations today, when facing some extreme problems, we have to pin our hopes on future ultimate theories. As a star candidate for the ultimate theory, string theory, though always controversial, provides a completely new perspective from mathematics for understanding the vacuum and even the entire universe. During research into superstring theory, string theorists discovered that our world should be 10-dimensional. But, from the perspective of relativity, even counting time, that's only for dimensions. Where did the other 6 dimensions go? Just as string theorists were at a loss, the Calabi-Yau manifold proposed by Chinese mathematician Xing-Tung Yau made everyone's eyes light up. Soon, they produced a paper titled Vacuum Configurations for Superstrings. String theorists believe that the dimensions of Calabi-Yau space, formed from Calabi-Yau manifolds, are different from ordinary 3-dimensional space. The dimensions of Calabi-Yau have a size and cannot extend infinitely. The reason the extra 6 dimensions couldn't be found was precisely because they were compactified into the microscopic Planck-scale Calabi-Yau space. Originally, everything seemed perfect. But, as expected, an unexpected problem arose. There isn't just one type of Calabi-Yau manifold. It is currently believed that their number, if not infinite, is still a vast astronomical figure. These different types of Calabi-Yau manifolds would form unique spaces with different physical laws. Which one our universe belongs to, no one knows. This bizarre result of string theory seems to suggest, from another angle, that a multiverse might truly exist. Therefore, in these different universes, they have different physical laws, including different concepts of vacuum. Level 7. The end of the vacuum. Nothingness. Actually, even before introducing Calabi-Yau manifolds, string theorists had discovered that some extra dimensions could only exist at the microscopic scale. Due to quantum uncertainty at the microscopic level, these extra dimensions also seemed unable to exist stably. In 1982, in a paper discussing the instability of Kaluza-Klein space, Edward Witten, later the father of M-theory, proposed a decay more terrifying than false vacuum decay. Witten discovered that in the vacuum described by Kaluza-Klein theory, once the extra dimensions shrink beyond a certain threshold, the vacuum would collapse into a point. At this point, dimensions would cease to exist. Here lies the end of the vacuum. Unlike the gravitational singularity of a black hole in 4-dimensional spacetime, the point formed by this decay, although starting as a point, would rapidly expand at the speed of light. More miraculously, even though it would grow larger, because it itself has lost its dimensions, to us, no matter how big it gets, it remains a point. This is the terrifying aspect of Kaluza-Klein vacuum decay. Compared to a black hole singularity, it doesn't just end spacetime. It also allows this end to spread to the surroundings, and compared to false vacuum decay, this decay doesn't just change the state of the vacuum. It directly annihilates the vacuum itself. If the space formed by the Big Bang is only the narrow space we are familiar with, then the end of space e that even any form of space in the broad sense will cease to exist. Could this be the legendary nothingness?